Our next speaker is a substitute. Professor Goodpaster was not able to make it, so he has sent a very capable substitute in Cheryl Szkudlarek. And Cheryl is a graduate student under Dr. Goodpaster, and she's going to talk about discrimination of dyed fibers based on UV visible microspectrophotometry.
Thank you. As you said, my name is Cheryl Szkudlarek. I'm replacing Dr. Goodpaster. The objectives of this research was to obtain a collection of dyed cotton fibers, take spectra using the MSP at 2 different laboratories to do an interlaboratory study, to carry out statistics on this data, and then form a spectral database. Here are a few questions that we can answer. The main ones are going to be how many classes can these dyes be classified into, what features of the spectra are being the most giving the most variation and the most discriminating between these dyes. So why study fibers? Fibers are important. They're widespread in the environment. As you guys sit in these chairs, you guys are leaving fibers behind. These fibers can be classified into main groups and subtypes that are physically and chemical differentiable. Key characteristics looked at are morphology, such as the diameter, the cross-section, and as you mentioned earlier, they use PLM to look at other characteristics, such as like the interference colors. They can also look at bulk composition, and most important for this study is going to be color. So how do we get the color? We use dyes. Dyes are a colored substance that is able to absorb and reflect certain visible wavelengths of light. There are thousands of dyes produced worldwide. And there are many classifications. How we are classifying our dyes is by method of application. Here are a list of the available dyes. The most important for this study is going to be direct, reactive, and vat dyes. Direct dyes are directly incorporated into cellulosic fibers like cotton using heat and electrolyte. Reactive dyes are they form covalent bonds within the functional groups of the fibers. Again, it can be used on cotton because our primary study was done on cotton fibers. And for vat dyes, they are generally insoluble, so they require a reducing agent to make them soluble, where they can be applied to the fiber, oxidize, and become insoluble. Here are a list of the dyes used in the primary study. These 6 dyes or exemplars were provided from test fabrics. The bottom shows pictures. It's hard to see the contrast, but already you can see some of the dyes are standing out. Like you've got C, which was a brighter red than the rest. D, right here, is a deeper pink. And A was like a standard red color. And then B, E, and F were slightly lighter pink. Here's just a brief intro on how you would look at analyzing fibers. You start with microscopy and look for general characteristics, determine whether it's natural or synthetic, and then you'd go to like microscopy to look at color and other such characteristics. Both of these are non-destructive, so that's why they're at minimum sample prep, so they're preferred. And you can look more intensively at the color or the dyes based on chromatography and mass spec, but primarily we're focused on spectroscopy. For sample prep, we had 6 dyed exemplars. We took 10 fibers per each dye, mounted them in glass microscope slides, and then took 10 scans per fiber using the MSP. For data analysis, the samples were truncated to a wavelength range of 350 to 800 nanometers. For background subtracted, we subtracted the minimum from each value. Normalization by square root sum of squares. And then we ran chemometric techniques. We ran agglomerative hierarchical clustering, principal component analysis, discriminant analysis, and analysis of variance. Here's just a look at the representative spectra for each of the dyes. Already you can see some characteristics are slightly different. Like reactive red 123, its wavelength max is slightly shifted to the left. You can also see that reactive red 120, reactive red 2, and reactive red 228 have like a double hump going on. The first analysis was hierarchical cluster analysis, or AHC. We use this to present the data in a way to emphasize groupings so we can get kind of a feel for how the dyes are being separated and what are the similarities. This also helps us detect outliers and possibly unique fibers within the sets. For this, the algorithm calculates and compares the distances between each samples, so the closer or the smaller the distance, the more similar our samples are going to be. For this, the result is a dendrogram, which is kind of like a tree diagram. You also will see a vertical dotted line, which is the truncation line. This is determined by when they're grouped together, these distances, when there's a huge group or a huge gap between these groupings, that's where the truncation line is going to be, and that's how it tells you where how many major groupings you're going to have. So for our 6 dyes, we had 4 major groupings. It's kind of hard to see, but I have green boxes around the fibers that were 10 clustered together. You see that right here. That's reactive red 228. All 10 fibers were clustered together, because for AHC, we used the average of the 10 scans per fiber. Reactive red 195 was in a group all by itself, and all 10 are clustered right here. Reactive red 123, which was that bright red one, also it's classified as its own class, and all 10 are clustered together. We noticed that for reactive red 2, it's split between 2 classes, but the majority of it is in the upper class right here, and 2 of them are clustered right here with the red box around it. So we looked back at the original, or here's just a summary of the classification, just in a way that most people can understand. And then we looked back at the spectra for fiber E, since it had 2 unique fibers classified in a different class, and you can kind of see that. You see that the red dashed lines, which are here, that was the unique fibers. Only those 2 from the 10 fibers were separated, so we decided to call them unique. The second analysis is principal component analysis, and the purpose of this is to reduce the dimensionality of our data, because right now the dimensions are way too many. It's kind of hard to look at. This also helps us detect patterns and outliers. The algorithm forms new axes called principal components. These want to optimize the variance between the data within the data set, and for the first principal component is going to contain the most variance, and then the second and third, they're going to be like the next most variance, and etc. So essentially what you want to be able to say is within your first few principal components, you have a representation of most of your data. The result is an observation plot, which is a 2D plot of the first 2 principal components. We also look at a factors loadings plot, which is going to tell us which areas of the spectra are contributing most to the variance. Here is the observations for the 6 dyes. The colors are kind of hard to see, but again, you have your reactive red 123 off by itself, and you also start to see that direct red C380 is also kind of separated. It's right here, but it's only a small separation. Then the rest, it's kind of hard to see where one starts and one ends. So we tried doing a 3-factor varimax rotation to see if we can get it in a better view, which you can. You can start to see more separation between the dyes. Up here, reactive red 123 is now up here, because PCA likes to sometimes flip it on you. Reactive red 195, which was the other dye that was in a class all by itself, is also, you start to see it separating from that huge group that was in the center. This is our factors loadings. To determine what ranges were the most applicable to variation, we did the 80% rule, so wherever it crossed 0.8 is where we determined what attributed most to the variance. Our positive correlations can be seen here and here, and our negative correlations can be seen right here. I overlapped these regions on the representative spectra just to give us an idea of how it looks like. You can see that for PC1, which is in blue, you see the positive correlation is right here at the beginning where they start to absorb, and the negative correlation is right here at the apex of reactive red 123. For the second principal component, you can see that the positive correlation is kind of on the rise and fall of the dip right there, and the negative correlation is almost on the opposite side of the max wavelengths. The third analysis is linear discriminant analysis, or DA. So the other 2 techniques are unsupervised, meaning that you don't have to input any group ideas, or you don't have to know anything about where the dyes are going to be placed. For discriminant analysis, it's supervised, meaning we're assigning these dyes and these fibers a distinct grouping, and we're trying to test out that model and see whether or not we're getting the most discrimination. And this also helps us detect patterns. Again, it forms new axes called canonical variates. These are set to minimize the within the group variance and maximize your between the group variance. So all 100 scans from one dye, essentially we want to be really clustered together, but we want that 100 scans to be completely separated from the 100 scans of another set of dyes. Again, the results are an observation plot, which is a 2D plot of the first two canonical variates. And we also get a confusion matrix, which is a summary of our reclassification accuracy. So here's for the 6 dyes. You can see reactive red 128 again off by itself. The direct red is also off by itself right here. And here's the direct red 195. Here is our reactive red 2 that was split between the two classes. You also see kind of that split going on. Up here you see one of E10, which was one of those unique fibers, and off to the side right here is the other one, which was E6. So we look at our confusion matrix. The top confusion matrix is when we classified we assigned each dye its own group. So there was essentially only 6 groups. Our classification accuracy was 85.25%. You can see that the direct red C380 and reactive red 123 was classified correctly 100% of the time, so that's excellent. But you also see reactive red 2 was only classified 59% correctly most of the time, which isn't so excellent. The bottom table is when we assigned each fiber its own class. So now there's 60 classes. Our accuracy increased to 92.13%. And again, direct red C380, reactive red 123, and now reactive red 195 were classified correctly 100% of the time. And reactive red 2 also increased. So now it was classified correctly 87% of the time. Our last analysis was the analysis of variance. This is to help us determine what regions of our spectra are giving the most discrimination. And for this, F values are determined, which is the ratio of the between group variance over the within the group variance. And the plot for this is a Fisher ratios plot. The higher the value, the more there's a difference between spectra. So here's our Fisher's ratios plot. You see that there are 2 main peaks. So again, we use the 80% rule and determine pretty much the range of what's going to give us the most discrimination. Here it is overlaid over our representative spectra. And as you can see, it's kind of on the rise and fall edges of the apex, or on the max wavelengths. We also did an external validation study. So we took 2 more fibers from each of the dyes and ran it through MSP, and then ran it through with the data sets. This was done by another analyst. For the sake of time, we're just going to show you what it looks like in the discriminant analysis. You can see that they clustered pretty well with the already pre-assigned groups. Again, we have it classified according to 6 classes and 60 classes. The accuracy kind of decreased when we gave each fiber its own class, from 82.5% to only close to 81%. But again, you can see direct red C380 was classified correctly 100% of the time for both fibers. Same is said for reactive red 123, and even most of the time reactive red 195. Reactive red 2, which was the one that was split between 2 classes, we saw that those 2 unique fibers were classified as itself 100% of the time. But here, the reactive red get kind of confused with the reactive red 120 and reactive red 228, so its accuracy is much lower. We also did an interlaboratory study. So we took the same analyst, went to both laboratories. We did it at IUPUI, and we also went to the Indiana State Police and used their instrument. The sample prep was the same, except we added 6 more dyes. These 6 dyes were provided from Dr. Stephen Morgan from the University of South Carolina. Again, you can see pictures at the bottom. Now we have 2 direct dyes and 8 reactive red dyes and 2 vat red dyes, which are K and L. You can kind of see in the pictures, which again, sorry, it's hard to see, but fiber G, which is right here, it had more of an orangey brown tint. And this is going to be seen through all the analysis. And then the same can be said for, again, A through F, it's the ones that you saw before, so the same characteristics apply. For K and L, it's slightly lighter in color, so it's more translucent. For the sake of time, we're just going to show you the discriminant analysis results. You can see that reactive red 123 was classified correctly 100% of the time at both laboratories, as well as direct red 84 and both vat red dyes. When we did AHC, again, we had 4 major classes, with direct red 84 being classified with reactive red 123, and both vat red dyes were in its own class. The accuracy at IUPUI was 85%, and the accuracy at ISP was 81.25%. So that's not a huge difference. You do see some discrepancies, which are highlighted in red. You see reactive red 195 at IUPUI was 72% correct, and at ISP it was slightly higher. But then it balances out with reactive red 198, where at IUPUI it was classified correctly 92% of the time, and at ISP 70%. So conclusions. There were 4 main classes in our main training set. 67.51% of total variance was captured for the first PCs. You saw some dyes like direct red, C380, reactive red 123, and 195 were correctly classified 100% of the time, and that's really encouraging. Our overall accuracy was also above 90%, and that's really what you want to see. The wavelengths of most discrimination are listed here, but just as, I don't know if you guys remember from seeing it briefly, but it was on the rise and falls on the other sides of the apex. We also saw some uniqueness within the fibers of reactive red 2, with the 2 fibers being classified in class 1 and the 8 being classified in class 2. For the external validation, the overall classification accuracy was above 80%, so it's not great, but that's still good enough for our analysis. And for the interlaboratory study, we saw that the 5 dyes were readily distinguished using both instruments, so there is consistency between instruments. Both direct red dyes stood out, as well as both vat red dyes and reactive red 123, which you saw earlier, also stood out a lot. The remaining dyes, however, were not. Although the degree of confusion between laboratories varied, overall it pretty much equals itself out, though. We'd like to thank ISP, Dr. Stephen Morgan, Tom Klaus at Test Fabrics, and the MFRC, who funded our research.